In section 6.3, we're going to go over how to divide two polynomials. In the previous sections 6.1 and 6.2, we've gone over how to add, subtract, and then multiply polynomials. So in this particular section, we're just finishing up with the four basic operations, and that would be division of polynomials. Now, before going over how to do division with polynomials, I thought we'd first review how do we divide two numbers, and more specifically, how do we divide two numbers without the use of a calculator. And if you recall, way back when you were younger, maybe 4th grade, 5th grade, you started to learn division and you did long division. So that's what I'm going to go over, is how do you do long division, so we can apply this then to polynomials in just a moment. So dividing, we take 7 into 16. How many times can 7 go into 16? And the answer is 2. And then whatever's on top up here will multiply the number in front. So 7 times 2 makes 14. And then we subtract. So 16 minus 14 is 2. We bring down the next number 1. And now we repeat the process. 7 goes into 21 3 times. 7 times 3 is 21. Take away, and we get a remainder of 0. In other words, 7 divides into 161 23 times evenly. Nothing left over, no fractional part left over. Okay, what about the next one? 277 divided by 12. Well, 12 is a 2-digit number, so we take these 2 digits into the first 2 digits here. So 12 goes into 27 2 times, and then we multiply 2 times 12, we get 24. We subtract 27 minus 24 is 3. We bring down the next number 7. 12 goes into 37 3 times. 3 times 12 is 36. Take away, we get 1. Now there's nothing left to bring down, so the 1 represents our remainder. So the question is, how do we write that? What we don't write is 23 remainder 1. That's not good enough. And I suppose if we wanted to, we could show how we can add a decimal point and a 0. We can bring down and we can figure out what the decimal value, 23 point what, is. But we can also write this remainder just as a fraction. The best way to write this, so if we're not going to write it like this, we're going to write it as 23, and the remainder is 1 over the divisor 12. Okay, so 23 and 1/12 is the answer to this division problem. So that's how we represent the remainder. This is the remainder over the divisor. Alright, well now let's see if we can apply what we just did with long division of numbers to long division of polynomials. First thing to do is just to rewrite the problem. So I'm dividing 3x plus 1 into 15x squared plus 8x minus 12. So the first thing to do is to ask a similar question that we started with on the other slide, is how many times does this go into this? So we'll start with the first term here, the 3x. How many times does 3x go into 15x squared? Or another way to ask the question, and this might be the better way to ask the question with polynomials, is what can I multiply this first term by to get to this first term? Okay, and the answer would be that I would multiply 3 times 5 to get to 15, and I would multiply x times x to get to x squared. So I need to multiply by 5x. Now I'm going to take that 5x and I'm going to now, since it's above the bar, I'm going to multiply it to what's in front, and that's going to be a distributive property. Multiply it to both terms. So 5x times 3x is 15x squared, and 5x times 1 is a positive 5x. Notice I'm lining up all my like terms, all my powers. I'm lining up along the way, and I'm going to keep doing that on every problem. Well, what comes next, and this is the part that's kind of missed the most often, when we do the long division, whatever we have here, we need to now take away from this line. We need to subtract. So I need to subtract everything in this line from the line up above it. So I'm going to take away the 15x squared, and I'm going to take away this positive 5. So I'm making sure that I carry that minus into both terms. Okay? So 15x squared minus 15x squared is 0. Those cancel out. And 8x minus 5x is 3x. And we bring down the next number, which is minus 12. And now we do this all over again. So what can I multiply 3x by to get 3x? And the answer is positive 1. Positive 1 times 3x is 3x. Positive 1 times positive 1 is positive 1. And again, we're now going to subtract this term. We're going to subtract this term. So always carrying that minus to both terms. Okay? So 3x minus 3x is 0. Negative 12 minus 1 is negative 13. We can't multiply 3x times anything to get 13 as there's no x here, so this has become the remainder. Okay? So how do we write this final answer? How do I write this answer with remainder? Well, we'll write it like we did the similar problem before that had the remainder. The answer is going to be 5x plus 1 plus my remainder, which is negative 13, over my divisor, 3x plus 1. Okay? You might also see it written like this. 5x plus 1. Because the remainder is negative, you might see that negative pulled out instead of adding the remainder. I'm just going to pull that minus out, so minus the fraction 13 over 3x plus 1. Okay. Either of these would be just fine. This one on bottom, quite honestly, you're probably going to see more often if the remainder is negative, pulled out just like that. Next problem, another polynomial long division. This one is a little bit different than the last one, and if you notice, and I'll point it out to you here, why it's a little bit different. Right here, we are missing the y term. Okay. Notice that we've got y cubed, we've got y squared. Next in order should be the y term, and it's not there, and then we have the constant. So let me show you how you set this up when you are missing a term. So we're going to have y minus 3, and it's dividing into this polynomial, 2y cubed minus y squared. What we're going to do where the y should be is we're going to add a term in place. We're going to add a 0y and then plus 25. Okay, so very simply, we're going to hold the place. Hold the place with the 0. Okay, and you'll see why kind of as we do this and we do a variety of problems that it's important to have that 0 there as a placeholder for us. Alright, so we begin by asking the question, what can I multiply the first term here, y by, to get 2y cubed? And the answer would be 2y squared. 2y squared times y makes 2y cubed, and 2y squared times negative 3 makes a negative 6y squared. Now I'm going to next subtract each of these terms. So I'm going to minus this one, and when I minus this one, subtracting the negative, it actually changes this one to plus. Okay? Now adding together, the y cubes cancel, and the y squareds add to positive 5y squared. I'm going to bring down the next term, which is a 0y. And now I go again. What do I multiply y by to make 5y squared? And the answer is 5y. 5y times y makes the 5y squared. 5y times negative 3 makes negative 15y. Again, I'm going to subtract this line. I'm going to subtract this number and subtract on the negative, which changes it to positive. So the y squareds cancel, and you can see now why I wanted this 0y here, because I needed a like term for the 15y, which was going to be created. So I'm going to add that and get 15y. We bring down the positive 25, and we go again. What do we multiply y by to make 15y? And the answer is 15. So 15 times y makes 15y. 15 times negative 3 makes negative 45. And we subtract the negative, change to plus there. And so we get the y's to cancel, and we get a remainder of 70. So our answer is going to be 2y squared plus 5y plus 15. The remainder is positive, so plus the remainder 70 over the divisor y minus 3. That's it. Alright, one more to try. You might try this one on your own. If you're watching this video at home, you might pause at this point, try it, and then play to see if you got it right. If you're watching this in class, you probably just let it keep running. You might try and work ahead of me if you want. So the first thing to do is to go ahead and set this up. So I'm dividing x minus 3 into x squared plus 5x minus 28. Notice there was no missing power of x this time, so there's no 0 anything along the way here. So I begin. What can x multiply to make x squared? And the answer is x. X times x makes x squared. X times negative 3 makes negative 3x. I'm going to subtract. So I'm going to subtract this negative, changes it to positive. And so the x squareds cancel, we get 8x. And we bring down the next term, minus 28. Okay. And now we go again. What can we multiply x by to get 8x? And the answer is a positive 8. So 8 times x is 8x. 8 times negative 3 is negative 24. We're going to subtract the whole row. So distribute the minus to both terms. So the x's cancel, we add this, we get negative 4. That's now the remainder as there's no x. So the answer is x plus 8 minus, because the remainder is negative, 4 divided by x minus 3. Alright, on this next problem, you might begin by looking at this and saying, hey, that looks just like the last problem that we did. With long division, so we already have the answer to the problem, and you'd be correct in stating that. But if you look at the title, it doesn't say long division, it says synthetic division. What I'm going to do with this problem is I'm going to show you another way to divide polynomials. We're going to take a problem that we already have the correct answer to, so that we can kind of compare side by side what you have previously done with long division to this one with synthetic division, and you can kind of decide for yourself maybe the pros and cons between the two techniques. Maybe if you like this one versus the other one, long division, or vice versa. So let me show you how to set this one up. The first thing I do, just the setup's a little bit different. My division symbol, I'm going to flip upside down. And I'm making it wide enough here that I'm going to fit 2 rows of numbers inside here. Okay, so make it kind of longer than you would with the long division problem. Now inside the synthetic division goes the coefficients. Okay, so I want the 1, the 5, and the negative 28. So I'm just going to take those numbers, 1, 5, negative 28. So we drop all the x's. On the outside, similar thing, we're going to drop the x. We're not going to use all of x minus 3 out here. What we do is we take this x minus 3 and we set it equal to 0 and solve for x. If I do that, we get x equals 3. That's the number that we use on the outside. Okay? Students generally say we just take the opposite of this, and most of the time you'd be correct in stating just that. Okay. Now one other thing I'm going to add to my setup here, between the last 2 numbers that I have, I like to just add a bar here. What we're separating out is that this number right here, when we find it, is going to be the remainder to the division. Okay, so I'm just kind of separating that from the rest of the problem. So here's how we do this synthetic division. The first number, we just bring this down. So we just copy that below the bar. And then anything that's below the bar down here will multiply what's in front. So 1 times 3 is 3, and we're going to put that 3 in the next spot, which is underneath the 5. We're going to add these numbers together. We get 8. Now this 8 is beneath the bar, so it multiplies the 3. 8 times 3 is 24, and that goes in the next spot. And now we're going to add these numbers together. Negative 28 and 24 is negative 4. Okay. Now look at the numbers that we have here, the 1, the 8, and the negative 4, and look at the numbers we had in the long division. Okay. As far as the coefficient goes, it was 1x and 8, and the negative 4 was the remainder there too. It's the same numbers. What we have to do now is we have to add the x's back in. Okay. So here's how we add the x's back in. This first term here is 1 power less than, I'll say, what we started with. Okay. So in other words, we started with x squared. So this 1 right here has to be x to the first. Okay. So I'm going to write that. I have 1 x to the first, which is just x. And then after we establish that first power, and then every number after that just decreases the power by 1. So if this is x to the first, this should be x to the 0, and x to the 0 is just the constant 8. Now we've got the remainder, which is a negative 4 over, not 3, but the original divisor, which was x minus 3. And so we can see how these numbers here just represent kind of coefficients and constants of our solution. Alright, let's do a couple other examples to kind of further cement this new idea. Alright, so we're doing synthetic division on this next one. So again, I begin by flipping the division upside down. Inside here are going to go all the coefficients. Now notice in this particular problem, we're missing the x squared. So we're going to have to hold its place just like we did with the long division. So we have 3 for the x to the fourth. We have negative 1 for the x to the third. We have 0 for the x squared. We have positive 5 for the x, and we have negative 1 for the constant. And now that I've got this spaced out right here between the last two, I've got my remainder spot set up. Okay, now in front, what are we going to use out front? If you recall, we're going to take this x plus 2 and set it equal to 0 and solve for x. If I were to solve that for x, the 2 gets subtracted over, so we're using negative 2 out front. Okay, now here's again the procedure. The 3, we just copy it down beneath the bar. Now whatever's beneath will multiply to what's in front. So negative 2 times 3 makes negative 6. Now the numbers that are inside the bar vertically will add together. Always add together here. So negative 1 plus negative 6 is negative 7. Now we multiply these numbers together. Let's multiply to give 14. We add 0 and 14 together and get 14. We multiply negative 2 and 14 together and get negative 28. We add together here and get negative 23. We multiply together and get 46. We add together and get 45. And the final thing to do is to rewrite my solution now with all of the x's placed back in. So I started with x to the fourth, so this needs to be decreased by 1 power of x. So this 3 represents 3x cubed. And now we just go in order. Next is a negative 7, so minus 7x squared. And then a positive, so plus 14x and a negative 23. The remainder is positive, so plus 45 over my divisor, x plus 2. And that's it. So you can see the synthetic division is kind of just quicker. It's maybe like a shorthand form of division to do, where we just drop out all the x's, run through basically the division algorithm here, and then we throw all the x's back in at the end. Alright, one more to do, one more to try. This one just kind of you on your own, see if you can do this synthetic division. Again, I would pause this if you're at home and try it on your own. Otherwise, you might just continue to just watch this straight through. Inside my synthetic division bar is going to go 5, negative 4, and 12. There were no missing powers of x here, so no zeros needed. On the outside here, we're going to take the opposite of this 3, so negative 3, and we're ready to go. We bring down the 5, and we multiply together. We add together, and we multiply together, and we add together. That's it. Now we're going to throw the x's back in. We started with x squared, so we take one off. This 5 is 5x to the first minus 19 plus the remainder, which is 69 over x plus 3. Alright, the last thing that we're going to look at is called the remainder theorem. It's kind of an illustration or one of the uses of, I suppose, polynomial division. The remainder theorem says that if a polynomial function f of x is divided by, we'll say, x minus k, then the remainder is f of k. Okay, so polynomial function f of x is divided by a binomial x minus k. The remainder is just f of k. Okay, so let's illustrate that then with an example. Now, directions here say to evaluate using two different methods. Okay, so the first method, let's just evaluate this like we normally would. Okay, if you're given this problem in chapter 1, what would you do? If you're asked to evaluate p of x for x equals 2, you're finding p of 2, and we do that by substituting 2 in for all of the x's. So let's see, we'd have 2 times 8 plus 5 times 4 minus 2 plus 7. So this would be 16 plus 20. Let's go ahead and add these together, which makes 5. So that would be 36 plus 5, which is 41. Okay, so there's p of 2. Now what the remainder theorem tells us is that this number right here is the remainder. So is the remainder when p of x is divided by x minus 2. Okay. Why x minus 2? Because we've got to flip this back. This is, if you think the synthetic division that we've been doing, we are flipping the sign of the binomial because we set equal to 0. So I'm thinking to myself, what set equal to 0 would have given positive 2? It would have been x minus 2. Okay, so let's check and see, does this work? If I were to instead divide, okay, if I were to instead divide this polynomial by this, which is x minus 2, what do I get? And I'm going to do synthetic division because it's by far easier. Okay, so we've got 2 for x to the third, 5 for x squared, negative 1 for x, 7 there. So here's my remainder spot. We're dividing by x minus 2, so we're going to use positive 2 right here. So we bring down the 2 and we multiply. We add and we multiply. We add and we multiply. We add and we get 41. Okay. So you notice that just as the remainder theorem says, and it did happen, the remainder that we got is just the function value evaluated at this number. So what's easier to do? Was working through all these steps and following order of operations correctly, was that easier, or was this easier to just do repeated multiplication and addition? That's all I did here. I multiply, add, multiply, add, multiply, add, all the way until I got my answer. Okay. A lot of people find that this is a little bit easier. Okay. This is called synthetic substitution. Okay. Synthetic because it's synthetic division, substitution because we're doing this instead of substituting this number in for all these x's. So synthetic substitution is a way to evaluate functions for x values. And it's the remainder theorem that tells us that this is essentially this, that they're going to always be the same value.